Hello, welcome back to Unit 5 for AP Physics 1. This is our torque and rotational dynamics unit. So now we're going to start moving into that dynamics portion of our topic, okay? So the first thing, again, when we talk about laws of motion, we go back to Newton, right? So here we have rotational equilibrium. So this is going to be our Newton's first law, okay? Because remember, first law was inertia and equilibrium. So a system may exhibit rotational equilibrium without being in translational equilibrium. So this is our linear equilibrium, right? This is what our new topic, right? And so what happens is there's two conditions for an object to be in true static equilibrium, okay? And those conditions are the sum of the forces have to equal zero and the sum of the torques have to equal zero, okay? So an important thing to note is that you're going to have to create free body diagrams, right? Which, in fact, we're going to create these force diagrams, and the force diagram will show forces and torques, okay? So you're going to put those forces where they are being applied. So if I take this, bridge picture, right, I'm going to have, the weight of the bridge, and then I'm going to have these 2 points here and 2 points here, right, on the ends. These are going to be adding forces involved, okay? Now, we always assume that they're positive, but if you end up with a negative, that just means you assume the wrong, you pointed that original arrow in the wrong direction. That's not wrong. It's just how how it went. So rotational equilibrium is a configuration of torque such that the net torque exerted on the system is zero, okay? So this is rotational equilibrium, right? Sum of the torques equals zero and sum of the forces equals zero is translational equilibrium. And so rotational equilibrium means that there is a constant angular velocity. So what does that mean? Our angular acceleration equals zero. So we often look at it in terms of like everything is not rotating, but if I had an object that was rotating at a constant angular velocity, that means it is undergoing rotational equilibrium, right? So a lot of times they'll do these like window washers on a platform, okay, and the ropes are here. So if I'm doing a rigid body diagram or a force diagram, so sometimes I'll slip up and call them RBDs, which R stands for rigid, okay. I would have all the forces acting. In fact, those aren't the cables. The cables are on the outside. So here are cables, right? And if you have to solve these problems, easy thing to do is put your axis of rotation, right, at one of the points. Let me do a different color, right? At one of these points. This way you can eliminate that effect of the force on your rotation, and then it just becomes simple. You would use your rotation equation to find this, okay? And then you go back into your force equation to find this one, okay? Or you can shift it and do the other side, right? So you have multiple ways to solve these problems. All right, so let's look at an example. So one of the classic questions that shows up a lot is the ladder question. And so we're going to go over this. It's not going to take a lot of time on this problem, but just be aware of how this procedure goes, okay? So you have a ladder. It's leaning on a wall, right? It's a frictionless wall. And then you want to know what is the force of friction at the bottom to keep it from sliding. So if I draw my rigid body diagram, right, I have the weight of the ladder, and then I have a normal force here, right, on the ground. But I also have a contact point here with the wall, and the friction is going to be in this direction, right? I don't want the object sliding this way, so my friction has to oppose it. And so what we're looking for, what is the minimum force of friction needed, right, down here? And so if I do all of my, right, I write my, essentially, I'm going to write all of my forces. So sum of the forces in the x direction is equal to zero. Some of the forces in the y direction equal 0. And I don't want this to rotate, so some of the torques is also going to equal 0, right? And so just like we did with Newton's first law, or Newton's laws, we did draw, sum, solve, right? So this is my draw step. This is the start of my sum step. And then I go into my solve step, okay? Now, we're going to need each one of these because friction has normal force in it. Normal force comes from the y direction. So there's, and so I need all of this. So if I'm writing my forces, so I have force from the wall minus friction equals 0. So friction equals the force from the wall, okay? So now we write our y direction. So I have the normal force, okay, minus the force of the ladder is equal to 0. And so what does that become? All right, F normal equals the weight of the ladder, which is mg. And this one I can do quickly. It's 16 times 10. I'll just use 10. So I know the ladder has a weight of 160 newtons. Why is that important? Because if we had to break it down, maybe we had to find the coefficient of friction. And remember, friction is mu times normal force. Okay. Now we go to the other side with the torques. Torque is kind of our more complicated process, right? So remember, we need perpendicular distances. So I have this distance, and then I have essentially this distance, right? So note they are perpendicular distances, but we're going to use different things. But the great thing is, if you remember from geometry, we have triangles here, okay? And so the force by the wall, right, will be the full height. And then the force at the ladder will be just a portion of the height, right? And if it's a uniform ladder, okay, then the weight is in the middle of this object. So we can basically say that this distance in the ladder will be 2.4, okay? And an easy thing to do is set these two equal to each other. So the torque caused by the wall is going to be equal to the torque caused by the ladder. Now, why does the bottom left not worry about it? Because that's our axis of rotation. That's where we don't want it to rotate about. Okay, so I go in, I do plug in all my in, and so we have RW, FW equals RL, FL, right? And this is what I'm looking for because that goes over into my X direction. So FW is RL, FL divided by RW, okay? Now RL, the ladder is going to be 2.4 cosine 65. And we know that it has a force of 160 newtons. And then the other one is going to be 2.4 or 4.8 sine 65. Okay, again, the triangles that I know is what causes sine versus cosine, right? And so we now know that the force at the wall is 37.3 newtons. Well, that's going to be our answer because, again, that is the frictional force. Because this force and the friction force down here have to be equal. Okay. Now, maybe they added, this could be part A. Maybe in part B, they ask you for what is the coefficient of friction. So we would do, remember, use this equation. So we get F over mu n, or Fn. And so we would have 37.3 over 160. And I didn't do this. This is an added bonus question. So 37.3 divided by 160. And so the coefficient of friction would be 0.233, right, for this wall or for the ground here, okay? Now, how can they make this a little bit harder? They would put a person on the ladder, maybe the person standing up here, okay? And they would just say, okay, well, now what is the force of friction going to be? Or they would say, how high could the person walk without it slipping? So there's a multitude of questions past what you see here that they can ask. All right, so now in the next video, we're going to wrap up Unit 5 by talking about what happens now when we introduce in an angular acceleration.